All right, so good afternoon, everyone. So now we start with the first lecture of Kristan Jensen on wormholes in holography. Thank you.
All right, well, many thanks to the organizers for inviting me to come and lecture for the training week. It's great to be back in Florence. Alas, there will be no reconstruction, there'll be no quantum information in these talks, but I hope you find it interesting nonetheless. I guess last preliminary comment, I just got here yesterday. I've been absorbing, a day and a half's worth. I guess all of you have been here for 4 days. Good luck. We got a lot of ground to cover. The last introductory comment, this web address was just written up here. I think it's a Slack, whatever a Slack is, that's set up specifically for this meeting, I guess, is that right? For the whole thing, okay. So you can discuss amongst yourselves there. I'm going to erase it later when I need the space. All right, so the main question that we're going to be concerned with in these lectures is, broadly speaking, what is the role of the multi-boundary problem in the ADS-CFT correspondence? And what physics does it encode? This is a question that, well, it's an old one. Dates back to the beginning of ADS-CFT, as we'll see shortly. And it's one that's been, revitalized of late. It's been the subject of much modern activity. It's an ongoing research area. You'll see papers about it every so often on arXiv. But because it's an old question, that means we got to start with the history of it. And, what will probably happen is by the end of today, we'll get through our history, and then next time, tomorrow, just before the lunch, I'll get into some of my own contributions on the subject. We have to start somewhere with the history. The history of wormholes in quantum gravity is an old one. We have to start somewhere. I'm going to pick my cutoff, my initialization, to be beginning of ADS-CFT, not before. So with that in mind, the question that we're going to be concerned with over these lectures is, let's keep it easy. Let's talk about Euclidean version of ADS-CFT. And let's talk about the multi-boundary problem. So consider having a boundary with several disjoint components. 1, 2, n. And attaching some asymptotically hyperbolic regions to them. Asymptotically Euclidean ADS. And then, we sum over things that fill in those geometries. And the question is really, there's a series of questions that attack us all at once. The first question is, what do we even mean by this in string theory? What are we summing over? What kind of configurations do we include? What kind of geometries do we include? Are there non-geometric contributions? So what on earth is this over here in gravity? But then there's another question, in light of ADS-CFT, we expect this to be dual to something in conformal field theory. What is it? Long-standing question. A reasonable guess as to what this is that, say we talk about ADS5 times S5, type 2B string theory with n units of Ramon flux, then the natural guess would be that each of these boundaries, on each of them resides an independent replica, an independent copy of our dual conformal field theory. If our conformal structure over here is like G1 and G2, up to Gn, etc., then we would expect, that on each of these boundaries lives a copy of our dual conformal field theory in the presence of, that background metric, etc. That's just the metric part. There's all sorts of other sources for all their operators. This picture generalizes. So a natural guess then is, well, what is this in CFT? You would hope that this is, partition function of dual CFT on this space times partition function on this space, etc. On the grounds that, well, one way of saying it is the boundary of these spacetimes is, Well, it's a boundary with many disjoint components. And if you consider a conformal field theory, local conformal field theory, on a space-time with different disconnected components, well, there's no interactions coupling the degrees of freedom in those different sections. We're in Euclidean signature, so there's no notion of a state that can entangle them. Things should factorize. But then, if that is indeed the case, we're immediately hit with some tensions, some confusions, almost immediately. And, well, the tension is this, you know, if I draw the same picture, but with a single boundary, instead of n of them, well, ostensibly, this is dual to a function of dual CFT on the one boundary. The same thing would be true for 2, 3, 4, up to n, in which case, well, we would have this picture with all these different throats attached to, filled in by something. Is in fact equal to something much simpler. And there's a question mark here. Is this the case or not in string theory? I guess I could draw several question marks, you know, to indicate that it's that it's unclear. So maybe another way of saying this is that our priors, going back to beginning of ADS CFT, are that, well, oh yes.
Could you state the precise string theoretic question that we are asking between the two cases?
Well, the question would be, you know, if we had some non-perturbative definition of bulk string theory, what is this, and what is it dual to?
Do you mean scattering of strings on that background?
What's that?
Are you saying scattering of strings on that background? Like, what is the precise question?
The precise question is how to say. I mean, what is string theory? String theory is a consistent theory of quantum gravity. If we ascribe these boundary conditions, maybe was one way of saying it. If we enforce those boundary conditions on target space string theory, well, what is that exactly? What's the definition for that? What configurations are maybe another way of saying it is, what's the integration contour? What configurations are you integrating over, summing over? Are we summing over topologies? Are we summing over non-geometric configurations? What is meant by letting string theory fill in those boundary conditions?
Right. So one would assume that, like, when you put the question marks over there, is the idea that you might have other contributions, but you're assuming that, like, the most naive assumption is that, okay, this may be the only contribution.
I mean, why do I say this is the naive
Yes.
definition? It's that, you know, if you just ask what is the boundary is, you know, something with many disconnected components.
Uh-huh.
Dual CFT should live on that space-time with disconnected components. No interactions between, you know, if it's local, there's no interactions between those degrees of freedom. The whole thing ought to factorize then.
Okay. Yeah.
That's the statement.
Perfect. Thank you.
Right, so maybe a way of saying this is that our prior, going back to beginning of ADS CFT, is that multi-boundary amplitudes, I mean Euclidean amplitudes here, ought to factorize and I use the word ought to kind of, you know, implicitly indicate that, well, you know, it's unclear. What's the right dictionary for multi-boundary amplitudes? We don't know. So, and do they or not? That's, you know, to properly address this question in the bulk, we need some non-perturbative definition of bulk string theory, which is presently lacking. And at some degree, it's an element of the dictionary, which we got to figure out. This picture is further complicated by the fact that, one way of saying this is that the connected part of this multi-boundary amplitude, according to this, ought to vanish identically. And it's not at all clear that that's the case. It's a very strong statement. For instance, we can at least draw field configurations, smooth geometries, off-shell ones, wormholes that fill in these boundary conditions. And if it's really the case that connected party is 0, somehow the sum over all those things that connect the different boundaries must identically vanish. Is that the case? So is this true? Is it not true? What does it mean if it's not? What do we learn about wormholes from this? Those are the broad questions that we will be concerning ourselves with in these lectures. Now, the first place where I saw this discussed in the literature as a problem in ADS-CFT, as something to be very confused about, goes back to before I was even a PhD student. The first place that I know of where I saw this discussed was in '99 in a paper of Witten and Yao. And because I was in high school at the time, I guess probably many of you weren't even born, which is horrifying. But well, some of you maybe, but I wasn't in the field at that time. I don't know if this was an ongoing conversation that led to this paper. I'd be very curious to hear from any of our more senior people if they can fill me in on the history of this. I've been reconstructing it from archive. The first place that I've seen this discussed is in a paper of where they observe this tension. What do? Well, they try to address it by asking the question, within supergravity, within low energy limits of string theory, are there connected geometries, saddle points, with multi-boundaries? And they prove a theorem. That theorem has a few limiting assumptions that you need to do to simplify the problem enough that you can make a theorem. What do they say? Well, what they say is that that's not theorem, this is theorem. What they say is, within Einstein gravity, i.e. no matter whatsoever, and ignoring higher derivative corrections and whatnot, with negative cosmological constant, and boundaries whose conformal structures have positive scalar curvature. So when you satisfy all of those conditions, there's no wormhole saddles. So what do you learn from this? With those boundary conditions, in this very simplified setting, there is no violation of the hoped for, desired for equal sign at the saddle point level. Yes? They do not exist with positive scalar curvature. We're coming to that. Yes?
How precisely are we characterizing wormholes here? Is it just disconnected, like fully disconnected asymptotic boundaries? Or
yeah, multiple asymptotic regions.
Okay.
With a connected geometry that fills them in. Like the total space-time is connected, but
Yeah.
the boundary has disconnected components.
Okay, and that can be, I imagine if they did it, it can be well characterized.
But what, sorry?
I imagine if they did it, this can be very precisely characterized and yeah.
Yeah. Okay.
Cool, thanks.
Right, so, great. Mind you, by the way, this is really in the early days. ADS-CFT dates back to, late 1997. And so, this is at the very dawn of the era. By this point, there were already like some significant number of precision tests that had been performed regarding the conjectured duality. But, now we have an even more impressive battery. So at this time, this was a real question. This would be a potential fatal flaw for the correspondence, and it was important that they checked. Yes?
But that seems to be like a purely gravitational, point of view.
Yes.
Why was there a tension? Because it may or may not happen that gravitationally you might have these saddles.
Well, so okay, one can. Why is there a potential tension? If such a saddle existed, if such a solution existed, then how to say, and it was stable, say, then you could worry. Well, how to say? Does this that would be a violation of the equal sign at the saddle point level, under the assumption that what you mean by this in the bulk includes the sum over geometries. And that would, yeah, go ahead.
But that's an assumption we make when we do quantum gravity. We sum over all geometries and topologies. And
Yeah. I mean, that's right. That's one of the assumptions that goes in that, how to say, another attitude that one could take, a possible attitude one could take is, look, don't sum over connected at all by hand. We just enforce that we don't do that.
Okay.
We don't know. Maybe that could actually, how to say, I think there's significant evidence by now that that's not what string theory does.
Okay.
But that's really a question about the off-shell, non-perturbative integration contour of string theory, which we are trying to kind of get at indirectly in these lectures.
Okay. Thank you.
Yeah. So we're already kind of seeing a feel in this topic that it is at once interesting, but vexing. What are the right assumptions? What are the right things that we should hold sacrosanct, and what are the things that we shouldn't? At some level, this is experimental mathematical physics. We're trying to figure it out as we go. Right, so this is a theorem, as is often the case, not always the case, but often the case when you have a theorem and it comes with certain assumptions. Once you violate the assumptions, you can find counterexamples. And those counterexamples, the first ones that appeared on arXiv appeared in a paper 5 years later by Maldacena and Maus. And the counterexamples, there's sort of two broad types. Well, one broad type and a specific instance. The first one, they're all two-boundary wormholes. The first one is you can take hyperbolic space in d+1 dimensions and quotient it by certain subgroups of the isometry group in such a way as to produce Einstein manifolds, non-singular Einstein manifolds, with two boundaries, not one, and where the boundaries are constant negative curvature manifolds, they're themselves quotients of HD. So for instance, if we were in 2+1, then the boundary would be two-dimensional, and these would be uniformized higher genus surfaces. Okay, and these are solutions to Einstein gravity. They can be easily uplifted to solutions in 10 and 11 dimensional supergravity. For instance, here you can simply let's just The only non-trivial field here is the metric. Everything else is trivial. So you can attach this, for instance, to, if we were interested in ADS5 times S5, we could make that a 5-dimensional hyperbolic space and then attach a 5-sphere everywhere and get a solution in 10-dimensional supergravity. There's a whole zoo of these. There's another exceptional case that they found where the boundaries that you have are spheres, 4-dimensional spheres. The whole thing has the topology of S4 times an interval. And, well, okay, this is like the 5D part of the geometry. This was a solution in SO6 gauged supergravity in 5 dimensions. The SO6 comes from reduction on an S5. So this thing has an uplift to 10 dimensions where it's asymptotically H5 times S5. And where the whole background is supported by a non-trivial profile for the SO6 gauge field. Meaning the 10-dimensional, one has a fully complicated 10-dimensional solution where there's mixing between the angles on the S5 and the 5 non-compact directions. And, well, what kind of profile does one have if you decompose SO6 into SO3 times SO3? The gauge background that supports this wormhole looks like an instanton in the first factor and an anti-instanton in the second on S4 at a particular point in instanton moduli space where the whole configuration is SO5 symmetric, where the SO5 rotates the boundary sphere. This is not the sort of thing you just casually think about, when you go back to your apartment at night after. This is a very non-trivial solution.
Quick question. It's probably a necessary detail, but just curiosity. What's the significance of the modulus of that discrete group there?
What is the significance of this?
Yes.
So if you don't have it, you just have like ordinary one boundary hyperbolic space.
Okay.
You need the quotient in order to generate multiple boundaries.
Okay.
And because this is a quotient, you can look in their paper to see discussion about it, and also in papers of Alex Maloney to see what kind of quotients these are. These are freely acting orbifolds. They don't have any fixed points. They have the effect of pulling the boundary apart and giving you 2 boundaries instead of 1.
Uh-huh.
But because all you did is an orbifold, you didn't change the Einstein tensor. You didn't change the curvature tensor locally.
Okay. Right.
And so these are still solutions to Einstein's equations with cosmological constant.
Perfect. Thank you.
Yes?
Sorry, can you just repeat in a second example which assumption of the theorem is violated?
Let's see. So in this case, boundary has negative curvature. In this case, there's a matter background.
There is a, sorry?
What's that?
Sorry, you said there is a matter background?
So here you have a matter background. That was pure Einstein gravity, meaning no matter turned on.
Oh, okay. So in the theorem, there is assumption that it's not only Einstein gravity, but it's pure Einstein gravity.
Pure Einstein gravity,
Oh, okay.
no matter whatsoever,
Okay.
yes.
Thank you.
Yeah, Nima. We have to wait.
So the curvature supposedly depends on the matter content, right?
This is
The curvature of the sphere.
the curvature here. This is the curvature in question. That's asymptotic, like boundary curvature.
Yes.
Yes.
So the spheres that you have over there, they have a curvature that's set by the matter content, right?
No. It's a choice. It's a boundary. What metric you put on the boundary is up to you. That's a boundary condition.
Okay. Sorry.
Okay. Good. I should start speeding up a little bit. So at this point,
And the SO6 gauge fields that you have here are not just coming from like the gravity in 10 dimensions, so it's not just Einstein gravity in 10 dimensions. That
yeah. This is coming from full type 2b supergravity with n units.
Cool.
Okay. Right. So, well, now there's a pickle because well, what now? What do you learn from this now? And, well, how to say? There was when it comes to this first class of wormholes, the ones with higher genus boundary or negative scalar curvature on the boundary, those actually you had a good reason to be skeptical of their status in string theory. Can I just? These, well, you might also be, how to say, so these you had good reason to be skeptical of, it turns out. I'll explain why in a moment. These, you should be very surprised at this point that this solution exists if you've heard anything about wormholes and gravity before. Famously, null energy condition forbids, in Lorentzian signature, wormholes that connect two very distant regions. And this is just ordinary supergravity, which respects null. So what happened here? How did that work? We'll comment on that shortly. Right, so the first, so let's see. So let's talk about this. Suppose, these kinds of geometries, they exist in any dimension. You could talk about a version relevant for the D1, D5 system. Or you could talk about, like what I'm doing over there, a version relevant for n equals 4, super Yang-Mills, both in type 2b. Let's focus on this for a moment. Now in this case, it turns out there is a perturbative instability of this two-boundary solution that you can't get, sometimes those kinds of instabilities you can get rid of by suitably orbifolding the internal space. In this case, you can't. I'm not want to talk about that further. There's actually a more severe instability that arises no matter what you did with the internal space, no matter what kind of dimension you have, that's worth highlighting. And there's a very general non-perturbative instability of these geometries. That it goes back to elements of it in a paper of Michelson, Maldacena, Strominger in '99 that were more fully fleshed out in a paper of Seiberg and Witten on D1, D5, all in '99.
Sorry, what do you mean by instability here, and why is that bad for including this in the path integral?
I'm about to say what the instability is and why it's bad. And,
thanks, sorry.
Yeah. What is the instability? Well, ignore wormholes for a moment. Let's talk about something more basic. N equals 4, super Yang-Mills in flat space is a very special quantum field theory. It is one that possesses a vast moduli space of vacua. Where the adjoint scalars of n equals 4 pick up vevs. A simple sort of part of the moduli space is one where SUN gauge group is broken. Gauge symmetries are not broken, it's Higgsed, to SUN minus 1 times U1. And what this corresponds to in a brane construction is the following. When you talk about n equals 4, you have a stack of n d3 branes up in 10-dimensional string theory. You've seen tables like this before? Some of you have, some of you haven't. Okay. Huh? Not happily. Okay. Kids these days. So it's hard to visualize 10 dimensions. That's the point of these tables. So when you draw something like this, you're saying, what are the 10 dimensions? 0 is time. Everything else is space. 3 branes. And then the x's denote which direction they're extended in. This is in 10-dimensional flat space. So you could draw as a picture, say, let those denote 0, 1, 2, 3, and then the other directions schematically 4, 5, 6, 7, 8, 9. The symmetric point in moduli space is the one where all n d3 branes are lying on top of each other. Well, let me... The one where it's Higgsed, partially Higgsed, is one where n minus 1 branes are here, and there's another isolated D3 brane living somewhere else. And then, if you look at the quantum field theory that's living on those D3 branes, you have, something with SUN minus 1. There's a U1 living on the one that's isolated, and then there's massive W bosons from strings that connect them. Okay, this is an old story. But this is, from this picture works even in ADS 5 times S5. What happens is, if you study vacuum ADS, Poincare patch, so flat boundary, ADS is some throat, there's a radial direction. What happens is that there are exact solutions for a probe D3 brane in this geometry where it sits at a constant value of R and at some point on the S5. How can that be? Well, there's a gravitational attraction that the brain experiences when it wants to fall to the bottom of ADS. There's also a Ramon-Ramon repulsion because the thing couples to the Ramon flux that puffs up the whole geometry. So there's a force balance basically that takes place, and it happens anywhere in the radial coordinate. So that's its gravity dual. Well, long story short, this force balance no longer works in curved space. It's a property of the flat space theory that it has this moduli space of vacua, but not in the curved space theory. So in other words, the curvature generates a potential on moduli space. What kind of potential do you get? Well, you can study, the potential that you get from a variety of angles, whether you look at a probe D3 brane in ADS or just from a microscopic consideration. It's, if we let this direction suitably understood the radial direction, call it phi, well, there's an effective action for that D3 brane that goes like derivative of phi squared in the boundary directions, where the conformal field theory is, plus a conformal coupling of that phi to curvature. This is in the regime where phi is very large, so that your brain is near the boundary, and there's subleading corrections at finite phi. Phi you can think of as the distance, the radial distance away from the stack of n minus 1 branes up in 10 dimensions. And, well, if this R here is supposed to be the boundary curvature, so if that's positive, that's a mass term. So for instance, if your boundary was S1 times S3, this is generating a positive potential. Your probe brane, it wants to sit at the bottom of ADS. You lift the moduli space. There's a single vacuum where the brane lives at the bottom of ADS. If R is 0, you have a moduli space. There's no potential generated. If R is negative, well, now we have a problem. This is a runaway. So so that's what happens. Now you might hope that when R is negative, that there's some way of stabilizing this, stabilizing the vacuum. For instance, you could try to add a deformation to n equals 4 that lifts the potential the natural candidate for doing so, if XA are the 6 real adjoint scalars of n equals 4, would be a deformation of this sort that's SO6 symmetric. This is an SO6 symmetric instability on moduli space. You might hope to lift it with an SO6 symmetric positive potential. At weak coupling, this, or in the free field limit, this operator has dimension 2. That's allowed. That's a relevant deformation of the model. You can stabilize this and end up with, so in other words, n equals 4 at weak coupling can be defined on a manifold with negative scalar curvature. But at strong coupling, famously, this operator is very heavy. It's not a light operator. It picks up an enormous anomalous dimension. This is the Konishi operator. It's dual to a fundamental string in ADS as opposed to a supergravity fluctuation. And its conformal dimension is order square root a 't Hooft coupling. So it's not a relevant deformation at all. You can't deform by it. There's no way of curing this instability. Yes?
Okay, I have heard the word Konishi operator before, but so how does this relate with the like strong weak coupling that Super Yang-Mills has, the S duality? Is there like a dual picture for this instability, or what's going on?
How to say, yes, there is an S duality of n equals 4. What you usually see when you've taken the, what's a way of saying this? The S duality flips the Yang-Mills coupling to 1 over the Yang-Mills coupling. But in the Maldacena limit, where we talk about ADS CFT, G Yang-Mills is always incredibly small. Remember, the limit is lambda, which is G Yang-Mills squared n, is much, much bigger than 1, but n is even bigger. So you're always in a regime of weak coupling from the point of view of S duality when we discuss this.
Yeah, okay. One other question, what kind, is this like a BPS, like a fractional BPS state?
This is exactly a BPS configuration.
This is BPS, so it preserves n equals 4?
Yeah, and it preserves the full it preserves the full supersymmetry. Of course, the conformal symmetry is broken by being out in the moduli space, but.
When you create brain configuration in Super Yang-Mills and you like separate a brain off, doesn't that usually like break some supersymmetry? Because
yeah. If you had how to say no, if you introduced like some extra operators, like local operators are always there are no local operators that respect the full supersymmetry that are fully BPS. You have half BPS, quarter BPS, et cetera. But these configurations preserve the same amount of supersymmetry as all the brains lying on top of each other.
Should that be obvious? Okay.
It's not, how to say, I'm stating these things fast because I have to get somewhere. The times have changed from when I was a student. In 2006 or so, or 7, when I would have been in a similar thing, yeah, okay, this was in the air and you know it, but times change. So,
just a very quick question. Can you give me some intuition on that action? Why do we have the Ricci scalar term? Like, why can't it be like minimally coupled or something?
Yeah. What happens? How to say the boundary scalar curvature acts as a source in Einstein's equations. It corrects the near boundary metric, and that correspondingly corrects the near boundary Ramon field. And then it's a computation. Yeah.
You say you would like to, for example, add this trace term to the Super Yang-Mills action. Is that legal from the, what does that look like from the worldsheet perspective? Am I deforming the string theory? What's going on if I...
That would be, well, how to say? How do you define string theory in this background is something that is beyond my pay grade? It's a Ramon background. So RNS superstring doesn't cut it. So what it looks like from the worldsheet point of view, I don't know. I'm saying what it would be from the quantum field theory living on the n equals 4, or sorry, on the 3 brains.
Okay, thanks.
Yeah. Okay. So okay. There's an instability of n equals 4. It can't be cured at strong coupling when boundary has negative curvature, That's true before we ever invoke the words wormholes or whatnot. And the way you see it is, in the bulk, the way that you see it is if you stick a brane here. I said, in flat space, there's force balance. In the curved space, what happens is there's not force balance. And it gets, you have a runaway. The brane is kicked out. It's up to infinity. That's true when you have a single boundary. It's true when you have multiple boundaries as well. So in other words, the dual conformal field theory in this case doesn't even exist at strong coupling with that kind of asymptotics. Correspondingly, these geometries are unstable to the nucleation of branes. D branes want to separate out and get kicked out, so D3s want to appear here. To preserve flux, the total amount of Ramon flux asymptotically, you would have an anti-D3 brane over here, and you want to nucleate them and send them out to the boundary and eventually screen the flux in between. The story for D1, D5 is a little bit more complicated than n equals 4 for reasons I can't explain in this amount of time. The short version is that these compactifications often come with moduli, and D1, D5 is no exception. There's a bazillion moduli associated with the compactification on like T4 or K3. And what can happen is that those moduli are such that if you go away from the point where they're all 0, if you tune away from that, which is perfectly legal, then you no longer have exactly BPS branes. You have almost BPS branes, where even in flat space, the tension, the sort of gravitational attraction and Ramon repulsion no longer exactly cancel. And in that case, well, what happens for D1, D5 is that you get a potential for where the brane is in ADS that dips down negative, but eventually goes positive again, very close to the boundary. So these geometries, what they want to do, even with a single boundary before having the second one, is so you have some effective potential is like a function of radial coordinate, and what it looks like is goes very, very far down, and then near the boundary eventually comes back up again. Potential is stabilized. So your brane wants to sit here at some particular value in the radial direction, anti-D1 brane, anti-almost BPS brane over here. So you might think that's okay, but, well, that's what happens for a single brane. Then in that background, there'll be a further instability for the next brane, and the next brane, and the next brane, and the endpoint of this non-perturbative instability is unclear. It's unknown. It's unknown even if you have a good geometrical description, semi-classical geometrical description of the endpoint of that instability. These brane nucleation instabilities, this is what they're called, brane nucleation. It's kind of analogous to Schwinger pair production in electric field, of charges in electric field. You'll see papers about this from time to time. It's an instability of backgrounds that goes beyond what you see from studying perturbative fluctuations of fields in gravity. It's something, if you will, that depends sensitively on the spectrum of extended objects that string theory hands you. Maybe a way of sharpening the statement is that in the context of D1, D5, one can choose orbifolds such that these wormholes are completely perturbatively stable. But yet, they have these non-perturbative instabilities as a result of being embedded into string theory as opposed to pure gravity. Yes? What, sorry?
Are there like bound state sort of thing in
because it's like a box. Yeah, I mean, your spectrum of fluctuations is like that in a box, roughly
Right,
speaking.
right. Also, the potential looks like I can have some.
Yeah. I mean, you can kick the brane, and it can, yeah.
Right, and even if I put multiple branes.
That's right. The problem is that it's, at the level of individual branes, you don't see a problem. The problem is that, if we, there's a Ramon flux that's supporting this, or, an NS flux if we're talking about F1 NS5 that's supporting this whole thing. And asymptotically, there's n units of flux, These things are like flux conduits when you uplift them to string theory. There's like flux running this way. There's n units of flux over here, n units of flux over here, but in between, well, now there's n minus 2. We have a jump. It's like analogous to a capacitor in freshman physics.
Right, right.
And well, now if you nucleate another pair and another pair and another pair, the amount of flux in between is decreasing, and that flux is what's puffing up the geometry and keeping it macroscopic compared to the Planck scale in the first place. So the concern that you could voice with these geometries is, well, what is the endpoint even a semi-classical geometry that is, ADS scale in the bottleneck? Or does it pinch off, for instance? And it's a field of ongoing research.
Okay.
Yes.
Perfect, thank you.
Okay. Okay, so much for these guys. What about this? Well, I'm going to proceed. Okay, so I said we should even be surprised about this background, that it even exists, given statement, doesn't null energy condition forbid wormholes? What's going on here? So what I'm going, there's a couple other known wormhole solutions of supergravity that have been found over the years that are sort of morally in the same class as this one. So let me proceed ahistorically and discuss like all of them at once and why they're even solutions in the first place. I guess it's implicit in what I'm doing. I'm trying to convey to you not just the history, but sort of it's a non-trivial business of finding and collecting a taxonomy of these solutions in the first place. It's very non-trivial business. All of the bells and whistles of string theory are coming into the game. So, right, so for that there's really only three sort of known wormholes of this type within string theory. There's that one of Maldacena mouse. There's another one that's asymptotically H3 times S3 times T4. It's found by Arkani Hamed, by Nima, a guy that I never met because he left the field, Orgera, and Polchinski from 2007. An axion wormhole. I'll explain where that name comes from. And an asymptotically H4 times S7 wormhole of Meroff and Santos from last year. And all these things have sphere boundaries, positively curved, and they have some kind of flux background. If you compactify on S5, or S3 times T4 or S7, you have a gauge supergravity in the remaining directions, and there's some non-trivial gauge profile that's supporting all these things. Here I said it was some SO6 almost instanton. I guess I should have said the total instanton number of this configuration is 0. It has an SO3 part and another SO3 part. All of these things sort of rely on the same mechanism for their existence, though. And that mechanism goes back to an old idea of Giddings and Strominger that gave birth to this whole literature on axion wormholes that you'll still see to this day. Well, all these things are sort of either axion wormholes or sort of more general notions of axion wormholes. Here's the basic idea expressed in bottom-up language, and then you can try to uplift it to string theory and bang your head for a while. So consider a simple effective theory of gravity, where you have gravity in d+1 dimensions, say a scalar, and a d-form field strength. And with an effective action in Euclidean signature, that looks like 1 over 16 pi g, d plus 1x, scroot g, minus scalar curvature, plus, say, an ordinary kinetic term for the scalar, plus, some kind of diatonically coupled p form. Those are the sort of theories that we're interested in. Well, a d-form, gauge field strength, can be dualized into a scalar. No, derivative of a scalar, rather. And statement is that the Einstein's equations, all the equations of motion of that model, are equivalent to those in a cousin model. In other words, these things are equivalent at the classical level to another action, S prime. I'm not sure what that is. Derivative of a new field, A, squared, and that's a minus sign, crucially. A is the so-called axion, and it's related to the original field strength by F mu1 mu d is e to the minus beta phi epsilon mu1 mu d nu d nu A. You dualize the field strength into an axion. Now, for those of you who have ever done these kind of dualization games before, you'll wonder about factors of I and the signs, what's going on. All I'm saying, to properly dualize in Euclidean signature, how to say there's an I that resides here. And that ensures that this ends up being a plus. And you transform something that has right sign, P form kinetic, or form kinetic term into one here. What I'm saying, though, is how to say, from the point of view of equations of motion, where you have steady configurations with real field strength, that'll correspond to a configuration in the dual picture with a real axion. And for that, effectively, the kinetic term flips sign. And that's how you evade null energy condition. You have wrong sign matter somehow, even though you started off with right sign matter.
I have a question. Sorry for interrupting your flow, because I want to go back to there. So you've been mentioning that we should be surprised about the solutions given energy conditions.
Yeah.
So my question then is, my confusion is, what conditions are we putting? Because, I would assume that if we don't care about energy conditions, then you can always create exotic matter. You could just define T mu nu to be the left-hand side of Einstein's equation. You can have any solution.
There is a whole segment of archive that does this, yes.
Okay. So, right. That's my confusion.
Yeah, but how to say, I am narrowing the scope of these lectures to what happens in string theory, where you have very specific matter content. It's not designer. It's not just up to you. It's handed down from above. Yes?
Sorry, I think you just explained this, but what's the if there is a physical intuition for introducing that sort of field strength and suddenly becomes negative energy?
What's the physical interpretation?
Yeah.
Yeah, it's, how to say, well, maybe here's the way that I think about it. One of these boundary directions, suppose that so in everything I'm talking about, the boundary is a sphere. But suppose our boundary was a torus, or something that has a Euclidean time direction. Mm-hmm. What this would correspond to is, well, in that case, if we have a time circle, then there's black hole solutions. Yep. In the Lorentzian signature. When you analytically continue those to Euclidean signature, there comes a very important factor of I. The gauge background that supports a charged Euclidean black hole the time component is pure imaginary. These are real. This would be analogous to like taking mu squared to be minus mu squared, where mu is coming, or charge squared to minus charge squared. That's the way that I think about it.
Okay.
Yeah.
Thank you.
But yeah. Okay. So, and what happens in string compactifications is that you have various moduli. You can phrase all those moduli in terms of scalars in the lower dimensional description. And when you do that by dualization, effectively, some of them, you can group all of this together. You can say that, look, there's some moduli space metric that is a right sign direction for moduli of sort of normal type, dilatonic type, and then wrong sign for the axions. The moduli space metric has indefinite signature, mixed signature. And well, what the axion wormhole of these guys corresponds to is you kind of exploit the time-like directions in moduli space, the things with wrong sign. And the mechanism that supports these is very similar. You have fluxes out in the boundary. It's more complicated, but it's the same idea, roughly. That's a lot of information. Thanks for bearing with me. What's the lesson? What do we take from reviewing this almost like zoo of solutions? What do we get from it? And perhaps the biggest thing that I hope you get from it is that it's not easy to find these configurations, and somehow they're very they're strange. They're exotic within string theory. It's not just like you can write down whatever matter effective theory you want, consider a bottom-up theory of gravity, and okay, have fun. String theory makes very specific, gives you very specific kinds of matter content, very specific kinds of low-energy effective field theories that almost, but not quite, lack these wormholes that would conflict with factorization. So almost, there's a very limited taxonomy.
Sorry, I know you just erased it. Oh, sorry.
Just one comment. I guess I should have said too, I wrote down these kind of limited examples. Those are sufficiently complicated that an exhaustive stability analysis has not been performed for any of them. So, I mean, there's almost no wormhole solutions, but there might not even be stable wormhole solutions in string theory. The jury's out. It's an ongoing subject of research. The thing that's on the best footing is the one of Merolf and Santos, and maybe that's unsurprising because of the people involved. They were able to perform a complete perturbative stability analysis that's sufficiently complicated that doesn't appear in the paper, but so I don't think it's been checked yet by anyone else, but certainly they have a good track record. The brain part of the story is completely unclear for them at this time. And the other wormholes, okay, it's just not known. Go ahead.
That's what I was going to ask. So all those wormholes, we don't know if they're non-perturbatively stable?
That's right. It's unknown.
Okay.
So whether or not there's even a factorization paradox at the level of saddle points within string theory is presently unknown. From the point of view of saddle points. So that's one lesson. But I've been talking about saddle point solutions to supergravity so far. And there's always this specter in the back of the room with a large knife or something wearing a cloak. What you could worry about, like, what about off-shell behavior of string theory anyway? We're talking about saddles. What about the non-saddles? What about the off-shell physics? How do we even begin to discuss that? It would have been sort of nice if string theory didn't even allow these wormhole solutions to exist and we wouldn't be worried about this in the first place, but that's not where we are. Again, it makes it, as a practitioner in the field, somehow very interesting and very vexing all at the same time. You're trying to piece it together. Now, historically, as far as I can reconstruct, the attitude in the aftermath of this activity was, I mean, maybe to put it uncharitably, but essentially, not to worry about it too much. I don't recall a single conversation about even these works when I was a student. I was a PhD student 2005 to 2010. I don't remember there being any discussions, at least at University of Washington where I did my graduate work. Maybe there were big ones ongoing elsewhere and people were worried about it, but I don't recall any major discussion in the field about these things. Yeah, there were other things to do at the time. And maybe the sort of maybe a bit of historical revisionism, maybe a bit of reconstruction is that, certainly from talking with people like Steve Schenker that were around, what was the attitude at the time? The attitude seems to have been like, well, maybe microscopic saves us somehow, and we just don't know how. Kind of like the words that you would say about black hole information paradox. The duality got to work, we don't understand how, we'll understand someday. Fast forward in time now. Significantly. All the way to 2018, 2019. There were 2 papers of Saad, Schenker, and Stanford, one in each year. That did very different things and kind of revitalized this subject. The 2018 paper introduced something that studied something called spectral form factor. In SYK model and in gravity, and introduced a very unconventional wormhole saddle in Lorentzian signature, not in Euclidean, called double cone, that I will have much to say about shortly. The 2019 paper was the one where they were able to study JT on any Riemann surface, essentially. They showed also that JT was dual to a matrix ensemble. That was the one that quote-unquote solved JT gravity. And for the purposes of this lecture, I'll talk about the second one first. I'll talk about JT first. Jeff already summarized what JT gravity is. I'm just going to assume that you're overwhelming experts on it by now. What is JT? It's a model of 1 + 1d dilaton gravity. It has no propagating excitations. Has no bulk gravitons. It can't in 1 + 1, but there's no propagating excitations of the dilaton either. There are, however, boundary degrees of freedom. You can think of them as boundary gravitons. And on non-trivial surfaces, there are moduli that got to be integrated over, as is familiar from worldsheet string theory. Different context. What did they do in that paper? They did a lot of things. One thing that they did was to compute the JT path integral over spacetimes of the sort that I've been drawing, multi-boundaries, where the surface to which they're connected, oh, hang on just a second, is a genus G surface. So these are, manifolds with n asymptotic regions that are all circles. They have Euclidean lengths, beta 1, beta 2, beta n, and where those asymptotically hyperbolic regions are attached to some higher genus surface. So these are genus G surfaces with n boundaries. Go ahead.
My understanding is that in gravity and field theories in general, we want to impose boundary conditions for the field. So what do you mean by dynamic, like degrees of freedom at the boundary?
Right, so there's various ways that one can discuss the boundary degrees of freedom of JT gravity. One way is to say, this is due to Maldacena, Stanford, Yang, is to say, what do you mean by the boundary? You're in the asymptotically ADS or asymptotically hyperbolic sense, you introduce a cutoff, and then you have a slice at fixed cutoff. You impose dilaton as constant there, and that there's some, in particular, constant and diverging. You impose that the length is fixed, also diverging, with a certain ratio held fixed. And then take cutoff to infinity. And what you find is that in a fixed ADS geometry, there are infinitely many configurations of the boundary that all satisfy those boundary conditions. With an action, this Schwarzian action, that you have to path integrate over with an appropriate measure. That's one way of saying it. Another way of saying it is that asymptotically you can put the metric into a certain form, and then there's if you fix like that you can undo this wiggly boundary, put the metric at fixed radial slice, and then you push that degree of freedom into the metric. There's a fluctuation of the metric that preserves constant scalar curvature that is subleading near the boundary, but it picks up an action. It's a large, the diffeomorphism that takes you from one to the other is a large one, and it carries an action.
Awesome, thank you so much. And we still have a well-defined variational principle even with these, okay, thanks.
Yeah, the 2016 papers that people cite on JT, the one of those guys, the one of mine, the one of Herman and friends, those are the ones to look at. Yeah.
Yeah, sorry, I missed. You were saying like before this paper, what was kind of the sense about like these weird wormhole solutions?
I think the sense was like, what are they good for anyway? And they shouldn't be there. Let's do other things. That's what I can, as far as I can tell.
Oh, just so like we were actually like trying to just kind of like rule them out, like they don't.
I mean, correct me if I'm wrong. Yeah. Do you have a question, or are you just holding the mic? Okay, perfect. Okay, great. So, God help me with the time. Okay, so these amplitudes, they can be computed. They can be written as a factor, a topological factor of e to the s naught 2 minus 2g minus n. That's an Euler characteristic term. And then there's a moduli space integral. These surfaces, they're all constant curvature. And they look like something looks like what's called a trumpet in this work, where there's a minimal length geodesic that is homologous to the boundary that has a length that you can think of as Bn, depending on exactly what conventions one uses. And there's an integral over those lengths, those are moduli, with an appropriate measure that you got to figure out. There is this intermediate surface you can think of as a constant curvature surface of genus G with these geodesic borders. And there's a moduli space of those manifolds that you got to integrate over with appropriate measure. There's a volume of that called Weil-Petersen volumes. And then times factors associated with the boundary degrees of freedom with each boundary. Beautiful formula. I can write it from memory. It's very simple. This thing has no saddle point approximation, by the by. You just have to, there's no saddle point to JT gravity of this sort. There's a bunch of off-shell metrics. In this case, you can fully enumerate them and fully integrate over them. That's one of the miracles of JT. But, okay, as should be clear from the way of writing this, these integrals, I guess it's not clear because I haven't said what these are. These are polynomials of finite degree. And therefore, this entire thing as an integral converges for any n and any g. These things exist. So there are wormholes in JT gravity. They exist. They're non-zero. You can compute them. You can enumerate them. And moreover, because of this large parameter S naught in the game, well, there's a suppression of these wormholes of increasingly higher topology. So you can be confident in this model that there really are wormholes, and consequently, there's a breakdown of factorization. It's an exponentially, the violation of factorization is by things that go like power series and e to the minus s naughts. These are very small violations of factorization, but they're still there. Those effects are non-perturbative from the bulk point of view. And it's actually, that's a very important clue. What you end up finding out, as these guys did, is that JT, well, it's a consistent theory of gravity. All these amplitudes exist. It's a consistent theory in its own right, despite not having strings or branes or any such things all in sort of the minimal version. You would expect it to have a dual description. It does. What is the dual description? It's an ensemble of random Hamiltonians. Where the dictionary, so there's an ensemble dual, a statistical average, and where, well, what is the multi-boundary problem dual to? This picture that I've been drawing. This is dual to an ensemble average of partition functions. This is beta 1, beta 2, beta n. Then this is trace e to the minus beta 1h, where h is the random variable that's being averaged. That's the random Hamiltonian in this matrix ensemble. You, then you. Or maybe you first, since you have a microphone.
So I understand that these are off-shell configurations. Why does it make them better from the standpoint of, like, you have to embed them in string theory if you want to say something about them actually existing, right?
This is the confusing. This is one of the things that's a bit perplexing about JT. Is you look at this, like, look, 2016 when these things came out, I thought to myself, having written one of the papers about it, like, oh, that's cute. But it doesn't exist non-perturbatively. Like, it's just nice as like a way, as kind of like a window into certain limits of string theory. This blew my mind when it happened. This work of wherever it is, Sodchenko, Stanford, that that these things exist on their own right without needing additional stringy modes. That this is a consistent theory of gravity on its own. Now, in that same paper, they discuss it. It's not 100% proven at this point, but it's probably true that JT is in some very extreme corner of the string landscape. So yeah, it is a string theory. But maybe we can discuss that maybe a bit later, how that plays with the story that I'm telling for the rest of this. But how to say? So can you use this to then discuss the problem that we were originally interested in, string theory on like ADS5 times S5? Short answer is no. There's a lot more, there's many more fields, there's many more, like as a baby thing that you could consider, as babies do this, you can consider JT coupled to a single scalar field. It's something that's very common in the nursery. I don't know why people use this language. So in that case, one way of, at the one loop level in the bulk, you would get an extra term here, which would be like partition function of that scalar field in this background at fixed values of moduli. That factor diverges in the limit where these necks pinch off and b tends to 0. I guess I should have said this. And, well then, as a result, these integrals, these moduli space integrals don't converge. You would say, we don't have a complete theory of gravity in that case. That's what I would have expected to be true. The fact that that's not what happens in pure JT is kind of remarkable. Yes.
So I'm just going to naively try to do this. So we have a double trumpet sort of, the wormhole would be, so that's a genus 0 to boundary.
Yeah,
so
that's the one exception to, well, there's two exceptions to this rule that I wrote down. Double trumpet is one of them. There you have a single modulus, a single b, not two.
Okay, my question is, why is it a e to the minus s naught suppression? Is there a parametric dependence of the integral on s naught, or?
This comes from the topological term in the JT action, which is independent of the moduli. It only depends on the topology of the underlying surface.
So then why is there a suppression of e to the minus s naught?
Because all of these geometries with, how to say, like if you compare the connected geometries to the disconnected ones, the characteristic is lower for the connected ones than for the disconnected ones. So So in other words, okay, so here's a picture. You could take Gina 0 if you wanted to.
Exactly.
But then you could compare this to the completely disconnected configuration.
Okay.
Where you have, but then all of these are filled in independently.
Mm-hmm.
And I guess this formula that I wrote, what I have in mind here is for a connected surface.
Okay.
For the disconnected one, this would be a factor of e to the n s naught rather than minus n.
Yeah, perfect. Thank you.
Okay, so that's the dictionary. That's how it is. But here's the extra thing. These wormholes, they don't simply exist in JT gravity. They encode physics. And this is the real point where you start paying attention. Did Brian talk about spectral form factor in his lectures? I wasn't here, so, okay. So no one's talked about spectral form factor this week? Shoot. Okay, well. Let me write it down. So, as a simple thing, limiting case of this, consider boundaries, sum over everything. This is going to be a disconnected part, where those are two hyperbolic disks, plus a connected thing that you were just saying is double trumpet, plus something with a handle in the middle. This is order e to the minus 2s naught. This is order e to the 2s naught, and this is order e to the 0 s naught. The double trumpet is the leading connected contribution to this, which you would say, according to this dictionary, is the average, ensemble average, e minus beta 1 h, trace e to the minus beta 2 h. That's an object people care about in different literature for very different reasons. Suppose we complexify or analytically continue the betas. You consider this. You could consider this object for your favorite Hamiltonian, or for the ensemble average of the Hamiltonians in the duality with JT, whatever you want. This thing is called, as a name, this is a spectral form factor. Spectral because it depends on the spectrum of the Hamiltonian. What are the players in the game here? Well, one way of saying it is you have two copies of your underlying Hamiltonian, and beta, which has the effect of tamping down the high energy behavior of that observable. If you have something like SYK where there's an upper bound in the spectrum, you don't need something like that. But if you're interested in quantum field theory where the spectrum is unbounded from above, you would want something like this to have a finite value for the trace. And this is some time evolution. Leads to phases. And if you were to write this for sum over spectrum of this Hamiltonian, there's a lot of interference that happens between those phases. The sort of picture that you get, let me draw a smooth picture and then what you would get for a single instance first. This is a whole talk in and of itself, so my apologies, I'm going to have to be very brief here. Okay. Where I should always label my axes. There's an XKCD comic about this. That's time, and this is called spectral form factor. the wiggly line refers to what you would get in a single instance. You get some horribly wiggly mess. The smooth curve that interpolates through the wiggly mess, that was useless. Well, that's the curve that you would get after averaging over couplings, having an ensemble average, or if you were to sort of smear in the energy domain a little bit. You don't exactly, how to say, when you have individually closely spaced eigenvalues, you smear over the levels, over the energy range by a little bit, but not very much. And these kinds of plots are universally expected for what are called chaotic Hamiltonians.
Sorry,
Yes.
just a quick question. That's the absolute value of your complex, because becomes a complex number, right? So what are you?
It's, well, because this H and this H are the same,
Oh, it cancels out.
this is real.
Oh, okay. Okay, sorry. You're
Excellent
right.
question. No, it's a good question. Yes.
Yeah, this is average over like a random Hamiltonian for H here.
In the context of JT, this is an average over suitable average over Hamiltonians.
Okay.
In the quantum chaos literature, where they had discussed these form factors for ages before, well, these kinds of averaging could either be over Hamiltonians, like random matrices, or for, you could also average in the energy domain. The expectation from that community was that if you have a complicated Hamiltonian with a dense spectrum of states, that at least this feature here and this feature here ought to be very universal, independent of the details of the microscopic Hamiltonian. In fact, there's an effective field theory description of those things. This is the so-called ramp, because it rises linearly. This is the plateau. It's ultimately due to the discreteness of the spectrum. There's an effective field theory description of this that relies on symmetries of the problem and is therefore expected universally to describe spectral form factor, even for very complicated Hamiltonians, not just random matrices. That effective field theory description, if you want to read more about that, you should look at recent papers of Altland and Sonner. It's an old effective field theory, but they give a very modern presentation of it in terms of, from the point of view of symmetry breaking. It's kind of like hydro for the form factor.
Excuse me.
Yes.
Very quick question. There where you wrote SFF, you're defining SFF as the ensemble average or the average over the window. So is, in that case, the SFF only the continuous line, not the
Yeah. What
right?
I mean, in a single instance, I mean strip off that. And what I mean for the smooth thing, I mean either with an average or with a suitable smearing. Yeah, Nima.
Can you get the smoothing by averaging over time?
Yeah, you can also, energy is conjugate to time, so you could also have like a rolling time average that produces this.
And the belief is that you produce this smooth curve for all chaotic systems.
That's the belief.
Okay,
it's not proven. There's a symmetry breaking picture, an unconventional symmetry breaking, and a sigma model associated with it that gives this. Right. So that's that. Its connected part is this, plus corrections. This right here, this amplitude. What is it? It's a very particular form. It's 1 over 2 pi, beta 1, beta 2 over beta 1 plus beta 2, which, if you plug in that analytic continuation and take the limit of large time, becomes T linear, which is what that is, over a long domain of time. I guess I should have said up to e to the s of that beta. So in other words, the simplest wormhole in JT gravity, this double trumpet, encodes a piece of physics that other people, suitably well informed at other points in time, would have told us that we should better expect this ramp. So the wormholes exist. they encode physics, at least in JT. And now, what does this mean for us, for the original questions that we started with? JT is not, string theory on ADS 5 times S5, so strictly speaking, it doesn't tell you anything, but that's what has led, one of the ingredients that has revitalized interest in these questions in the field. But, because JT is not ADS 5 times S5, you have to work harder you're inspired to work on the original question, but you got to work much harder. We started 6 minutes late, can I take? Okay. And I won't do the NEMA thing of just saying a few more minutes. Okay. So that's the 2019 paper. The 2018 paper, the one that presaged it, they were interested in the spectral form factor. In SYK and in gravity. SYK, random Hamiltonian. So what I mean by spectral form factor in that case is with the suitable average over, all-to-all couplings that defines what we mean by SYK model. In gravity, well, what were they looking at? They were looking at two boundary configurations in ADS. The sort of boundary conditions that you would want to prepare corresponding to this would have a boundary circle over here, boundary circle over here. If you have beta plus IT, beta minus IT, these are complex geometries asymptotically. You could ask, are there things of this sort in gravity? And are there saddles in particular of this sort? And for real beta, answer is no, there are not. For beta equals 0, there are. And that's the double cone. Roughly speaking, beta, if you could turn it on, would adjust the size of the geometry in between, but you have a Lorentzian cone point in the space-time that they consider. What are these double cones? These are saddle point solutions of Einstein's equations because they come as an orbifold of a solution that you know very well, two-sided black hole. Take two-sided black hole at some fixed mass. There's a killing direction. Orbifold by that time-like killing direction. By an amount big T. And just keep the exteriors. That's this. You can do that for any two-sided black hole. It's a singular configuration, but it's a configuration nevertheless. And, well, it's not only a singular configuration, it comes with moduli. You can do this for any black hole mass, any angular momentum, blah, blah, blah. And why are those moduli? Well, it turns out the action of this configuration, the classical action of this double cone is exactly 0. So those are tree-level moduli. So what they do, well, and because you have these two boundaries with these factors of t, you would say, oh, this has something to do with this. What they do then is to say, well, look, we got to get rid of these. They don't say it this way, but one way of rephrasing what they do is we got to fix the moduli. So what you can do is you can inverse Laplace transform this thing in beta. To fix a total energy. Say you do it with some window. Within a resolution, you fix the total energy, E, within some resolution delta. Where by that, what you really mean is the gravity problem with two boundaries. And what that amounts to doing, you find that there's a saddle point approximation to this, where beta is 0, where the geometry is the double cone, and where this fixes the mass of the parent black hole that you started with. It fixes the modulus. And so now you have some weird new saddle whose status is kind of unclear within string theory, because what happens, string theory has extended objects, and you can wrap those extended objects around the shrinking time circle very close to the tip, and then they become very light. They're sufficiently close to the tip. You need to include those in your low energy description, and then what happens? No one knows. And then, if you ignore all those issues and you just stare at the thing that you get, you take form factor, you do this to it, what you're doing really is you're getting a microcanonical form factor where you're fixing total energy to some range. And this result, this universal result for the ramp, in fact, according to that part of the literature, holds not only when you do this, but also when you fix total energy. So they would say, okay, you should still get T-linear behavior. Here, well, we have a saddle, so with 0 action. So this geometry gives you e to the minus s is 1. But then there's a 0 mode, where you can relatively translate one boundary to the other. That 0 mode leads to an overall factor in front of that path integral, so that this whole thing in the large T limit is some number, unknown number times T. Which is good. But it's also bad because, is this thing allowed? Does this exist in string theory? Is it healthy? Is it not healthy? So now you see sort of the tension. I've tried giving a talk, writing a paper at some level as an act of storytelling. This is the dramatic tension of the field. These wormholes, they give us physics, but at some level they shouldn't be there. And what gives? What do we make of all this? My last comment that I will make at the 7-minute mark, this is a 1-minute comment, and it's the end of the day, and we're all fried anyway, so this is a fun comment. Einstein gravity is connected in negative cosmological constant, admits a fun analytic continuation to Lorentzian signature quantum gravity with positive cosmological constant that has been studied over the years. If you want to know why, I can tell you after my 1-minute set. Lambda less than 0 Euclidean is related formally to some positive cosmological constant Lorentzian theory of gravity, otherwise known as de Sitter quantum gravity. And you can take all these pictures that I've been drawing about the wormholes, and you can draw the same kind of pictures in Lorentzian signature, positive curvature. Things like this. Where now time is running up, and these are asymptotically de Sitter regions. And in this case, there's no problem. You prepare initial conditions, you don't expect the universe to just end in thin air, it's going to keep going. In other words, these wormhole amplitudes in de Sitter are computing like S-matrix elements of this putative de Sitter theory, to the extent that this makes sense. That further complicates the story. We expect these kinds of amplitudes to exist in a good theory of de Sitter gravity, but they're very, as I've tried to explain, they're very strange from the point of view of proper ADS CFT. And it just adds one more wrinkle for us to think about. Yes?
So the de Sitter S-matrix.
So the de Sitter
S-matrix elements would be on the boundary.
Yeah. You can think of these things as preparing the in state and these as preparing the out state.
Right, but if we are living in a de Sitter universe, so we're living on those boundaries, for example.
Yeah.
Right?
Well, not here.
Well,
Not not infinitely far. Yeah.
right, exactly. So all the scattering like elements, matrix elements we'll calculate are on that boundary. Is there like a way that we can extract this information using scattering between these?
This is an ongoing field of.
Okay.
I mean, yeah. De Sitter holography how do we make sense of de Sitter quantum gravity is a very complicated and unclear subject. Long story short, but no, I mean, like, look, yeah.
This gives a stringy picture to it, right? Like, I've never seen de Sitter holography done from like a string theory point of view.
I mean, that's because it doesn't exist from a string theory point of view.
This gives a stringy picture to it.
This
right?
is well, what I said was not that like ADS5 times S5 analytically continues. Is that there's a suitable analytic continuation of pure Einstein gravity with negative cosmological constant, and you can couple some matter to it. And formally, there's an analytic continuation to de Sitter. But I mean, one way to see that this can't be the case in string theory is that lambda less than 0 vacua of string theory are supersymmetric.
Right.
This is going to break supersymmetry.
Oh, okay. Okay.
So this is not a string arrow. This is an arrow at the level of bulk effective field theory.
Okay. Cool. Thanks.
Yes.
So first question, actually on the below picture. Is the difficulty of constructing Euclidean wormhole solutions in string theory analogous to the problem of finding de Sitter vacua in string theory, given this sort of arrow?
How to say? Can you map those two problems onto each other? They're slightly different problems. Are they the same problem? It's a good question, actually. I don't want to say something wrong, so I will stop and I'll think about it. But I'm done, by the way, so I guess.
Thank you.
I was just going to ask about the matrix dual. So we now continue. What happens to the matrix dual for this?
Also a topic of ongoing research. There were a couple papers from 2019 on the subject. I can point you to the papers. So there was a paper of Maldacena, Turiachu, Yang. And then there was also one of myself, Jordan Kotler, and Alex Maloney. We got scooped by them, and we had to make up for it, so we wrote a lot more. But around, I think this is 1904 dot and 1905 dot, and in old. The idea, indeed, in those is to try to make some sense of analytic continuation both in gravity and in the ensemble, where, I mean, in one line, in JT, those boundaries correspond to, insertions of trace e to the minus beta h, with h the random Hamiltonian. Well, these would be like trace e to the minus I beta h, where beta is like renormalized length up here. Yeah, so from the point of view of the matrix model, provided that you include I epsilons, so as to have convergence, then those matrix model averages certainly exist. The issue that you run into in gravity is that, you need a definition for what you mean by the Lorentzian signature model. And in negative cosmological constant, so negative constant curvature, there's an enormous zoo of surfaces that are constant negative curvature, have as complicated topology as you like. Positive curvature, that's not the case. So you need to define what you mean in the de Sitter theory. Like, naively, there's just basically the sphere and things where you excise parts of this. But is that all there is, or what do you make sense of higher topologies? Like, in other words, what's the bulk definition whose genus expansion would coincide with the genus expansion of averages of these in the matrix model? It's unclear what that is. At the level of like sort of classical configurations in de Sitter, you can make some matches. You can relate those to averages of these. But beyond sort of classical configurations, it's unclear.
Hi. So this is going to be a very open-ended question, but I'd like to have your honest opinion. How much of this do you think is due to the unique and simple nature of JT gravity versus something more complex, but still maybe trivial? Well, not like two-dimensional Einstein gravity, but something like three-dimensional Einstein gravity.
Yeah.
How far do you think we are from computations like this to 3D gravity?
Come tomorrow.
Okay.
It's the short version. I mean, what's my honest opinion? I mean, it's an unscientific question, so I can give an unscientific answer. My unscientific, honest opinion is that JT is very good at what it's good at. In particular, it's not what is it there for? It's not there to tell you about the non-perturbative definition of target space string theory. It has other purposes in life. And it's very good at those purposes. But it's not telling you about how factorization works in proper ADS CFT. In proper ADS CFT, you have extended objects, you have non-geometric configurations to worry about, none of which are present in JT. But that's off the record. Yeah.
So you explained how the ramp part of the spectral form factor comes from this double cone solution. But the other universal part of the spectral form factor is the plateau at late times. So
ramp is also expected to be universal.
Yeah, I know that the ramp is universal, but I said the other universal part is also the plateau.
Yes, agreed.
So what happens? What happens at late times to guarantee the plateau?
In JT gravity, where you might have a prayer of being able to address this question, it's unresolved. From the point of view of JT gravity, how to say, there's like a bulk Newton's constant that's kind of swept under the rug because things are exactly soluble in the Newton's constant. And then there's also an expansion in genus. And from the ordinary gravity point of view, the expansion in Newton constant would be perturbative, expansion in topologies would be non-perturbative. JT gravity is non-perturbatively soluble, like in the genus expansion, but the plateau is a doubly non-perturbative effect. It involves resumming the genus expansion. In the matrix ensemble, the genus expansion is asymptotic, not convergent. So in other words, in gravity, now you're talking to the resurgence guys. In the matrix model, you can make sense of the plateau, because that's like giving you a doubly non-perturbative definition of JT. And in higher dimensional gravity, good luck. Does that make sense?
Yeah.
Okay.
All right, great. So I think we can end here for today. Thank you.